Triple integrals. In this problem, we're asked to use a triple integral to find the volume of this solid. The solid is bounded below by a cone and bounded above by a sphere. Notice that z is always greater than or equal to 0. And so for the section of the sphere that we are interested in, the sphere can be expressed as a function of z. Where do the sphere and the cone intersect? This will help me set up my bounds of integration. I set the two functions equal to each other, square both sides, get x squared and y squared all over to the right-hand side, divide by 2. And so the two surfaces are going to intersect when x squared plus y squared is equal to 9. And we are interested in all values of x, y, where x squared plus y squared is less than or equal to 9. So we're interested in the region enclosed by a circle of radius 3 centered at the origin. So when I set up my bounds, I see that y runs from the bottom of the circle to the top of the circle, and x is going to run from -3 to +3. Now z goes between the cone and the sphere. And as I said, y runs from the bottom of the circle to the top of the circle, and x runs from -3 to +3. So using these bounds, I'm ready to set up my integral. My first job is to integrate with respect to z. So let's do that. Integrate with respect to z. And then also remember to evaluate. And this is what you get. Now, this is a good time to step back and think about what's going on. At this point, it's going to be much easier to solve the problem using polar coordinates. So in the xy plane, we are integrating over a circle of radius 3 centered at the origin. And so switching to polar coordinates, r is going to run from 0 to 3, theta is going to run from 0 to 2 pi, and x squared plus y squared is replaced with r squared. And then don't forget to include that extra factor of r. So at this point, I'd like you to switch it all to polar coordinates. And this is what you get. Now notice that I have r squared, the square root of that. And that's just equal to r because r is running between 0 and 3. So I don't need an absolute value sign there. Let's distribute the r into the parentheses. At this point, I would break the integral up into two separate integrals. After I break it up into two separate integrals, it still looks fairly difficult. And so I'm just going to look at one piece of this puzzle, and that is the inner integral of the first double integral. I want to just look at that integration. Instead of using radical notation, I'm going to switch over to exponent notation. And I need to do a u substitution. Let u equal 18 minus r squared. And if I do that, du is negative 2r dr. And so instead of r dr, I'm going to replace that with negative 1/2 du. Do my substitution, and now this is fairly easy to integrate. After I integrate, I substitute back. So I have the antiderivative, and now I'm ready to evaluate. And when I evaluate, I get 9 times 2 radical 2 minus 1. Put that value, replace your inner integral with that value, and then let's go ahead and integrate the second piece. So when I integrate r squared, I get r to the 3 over 3. And then for the first piece, I just went ahead and integrated with respect to theta. And the second piece, I just simplified. I evaluated and simplified. And then let's integrate that last piece. And after we integrate that last piece, we just simplify. And so we're all done. The volume of the solid is 36 pi times the quantity radical 2 minus 1. You take care and have a great day.